Hi everyone, and welcome back to educator.com. This lesson is on electric potential difference, oftentimes called just electric potential or voltage. Our objectives are going to be to find and calculate electric potential energy and electric potential difference, to determine the potential difference due to a series of point charges, finding the electric field strength between two charged parallel plates, finding the energy stored in a parallel plate capacitor, and finally calculating the capacitance of a parallel plate capacitor. So, let's start by talking about electric potential energy. When we lifted an object against gravity by applying a force for some distance, work was done to give that object gravitational potential energy. By the same token, when you take a charged object and it's moved against an electric field by applying a force for some distance, you have to do work to give that object electric potential energy. Imagine we have a positive charge here. It's stuck in space. And a long ways away, infinitely far away, I have a little point charge. If I want to bring that point charge that's positive close to this big positive charge, I have to do work. I've got to push harder and harder and harder and harder and harder to get it closer and closer. Once it's in this position, it has a lot of potential energy, electric potential energy. It wants to be repelled because if I let go of it, it's going to go flinging off that way. It's going to convert that electric potential energy into kinetic energy. So we had to do work in bringing it from a long ways away until it was at this position. If we do work on an object, we have given it energy, in this case electric potential energy. Now the work done per unit charge in moving that charge through that electric field is a scalar, and that's known as the electric potential or electric potential difference if you're talking about the potential between two different areas. The units are volts, which is equal to a joule per coulomb, and the work done is equal to the change in the object's electric potential energy. So electric potential energy is charge times electric potential difference. So let's start off with the problem. If we have a potential difference of 10 volts between 2 points A and B in an electric field, what is the magnitude of charge that requires 2 times 10 to the minus 2 joules of work to move it from A to B? Well, let's start off with our givens. Electric potential difference, V, is 10 volts. Our electric potential energy is going to be 2 times 10 to the minus 2 joules, because that's the amount of work we had to do. We're looking for charge. Well, if electric potential energy is Q times V, then that means Q must be electric potential energy divided by V, or 2 times 10 to the minus 2 joules divided by 10 volts, which gives us a charge of 2 times 10 to the minus 3 coulombs. Pretty straightforward. Let's take a look at electric energy. How much electrical energy is required to move a 4 microcoulomb charge through a potential difference of 36 volts? Well, our charge now is 4 microcoulombs. Microcoulombs is 4 times 10 to the minus 6 coulombs. Our potential difference, V, equals 36 volts, and we're looking for electrical energy. Electrical energy is charge times voltage, which is going to be 4 times 10 to the minus 6 coulombs times our voltage of 36 volts, which implies that our electric potential energy will be 0.00014 joules. Oftentimes, when we're dealing with very small charges, something like a joule isn't a very convenient form of energy. We're talking about things times 10 to the minus 15, 16, 17, 18 joules. It's just not very convenient. So there is another non-standard unit of energy that's very commonly used. It's called the electron volt. It's given the symbol E capital V, and it's a very small portion of a joule. It's the amount of work done in moving an elementary charge through a potential difference of 1 volt. So if you were to think about it, if electric potential energy is charge times voltage, and your charge is 1 elementary charge, and you move it through 1 volt, the electric potential energy is 1 electron volt. If we were to do that in standard units, we would have said that This is the charge of 1e is 1.6 times 10 to the minus 19 coulombs times 1 volt would have given us 1.6 times 10 to the minus 19 joules. These have to be the same. Therefore, 1 eV equals 1.6 times 10 to the minus 19 joules. It's just another unit of energy that you oftentimes use when you're dealing with very small charges. Keep in mind, though, if you're going to use these values for energy in other formulas, the SI unit, the standard unit that's going to make all your units work out, is still going to be joules. That's the standard. A proton is moved through a potential difference of 10 volts in an electric field. How much work in electron volts was required to move this charge? Let's look at how easy this can be if we use electron volts. If our charge of a proton is plus 1 elementary charge, our potential difference is 10 volts, then the electric potential energy is charge times potential difference, or 1e times 10 volts, which is 10 electron volts. Very straightforward. If we wanted to do that in joules, we could have done 1.6 times 10 to the minus 19 coulombs times 10 volts would have been 1.6 times 10 to the minus 18 joules if we went through all that. Or we could have converted electron volts to joules when we're all done, knowing that 1 electron volt is 1.6 times 10 to the minus 19 joules. Thankfully, this problem made it nice and easy, though, in telling us that the answer was going to be in electron volts. All right, let's talk about equipotential lines for a minute. When you talk about topographic maps, if you've gone hiking or were in some sort of surveying organization, you've probably seen a topographic map where you have lines that show you areas of equal altitude. Those are lines of equal gravitational potential energy. We have the same sort of thing in the electrical world. We have lines of equal electrical potential, which we call equipotential lines. Now, equipotential lines always cross electric field lines at right angles. And if you move a charged particle in space, as long as you stay on an equipotential line, you don't do any work. Now, as equipotential lines get closer together, the gradient of the potential increases. You have a steeper slope of potentials. Kind of like if you have a topographic map and your equal altitude lines get closer together, you're looking at a steeper cliff, a steeper gradient. So what I'm showing here on the right is a positive charge. We have the electric field lines, which we've done before, the black lines radiating away from the positive charge. Our equipotential lines must cross them at right angles. So everywhere that an electric field line intersects an equipotential line, we have a 90-degree or a right angle. And equipotential lines show lines of constant potential. So if I were to take a charge, let's put a charge right here, and I want to move it over to here, somewhere else on the same equipotential line. The net work done is going to be 0 because you end up at the same potential energy, the same potential, because you have the same charge. Let's take a look at how we could draw some equipotential lines. Around positive point charges, they're pretty easy because it always intersects at a right angle. These must look like circles. So I'll do my best to draw a circle here. That would be one equipotential line. We could probably draw another equipotential line here. Pretty close. And in a perfect world, all of those would intersect at 90 degrees. Around a negative point charge, we'd have the same idea. Crossing all the electric field lines at right angles. So we'll get a circular pattern for our equipotential lines. Over here in the bottom left, where we have our dipole again of a positive and negative charge, well, now our equipotential lines get a little bit more complicated. The one right here is pretty easy. If we draw an equipotential line right through the middle, that's pretty straightforward. Crosses all of those at 90 degrees. But in order to cross all of these at 90 degrees, as we move in here, we're going to have to adjust that a little bit, and we're going to start to see some curve to it. So there's an equipotential line on that side. And on the other side, we're going to have the same sort of thing by symmetry. Try and cross all these as best I can at 90 degrees. And we'll get an equipotential line that looks something like that. And over here on the right, now again we have two positive charges. Let's see what we get here. Again, right down the middle, going to have that point where we don't have anything. But as we go just a little bit off here, we're going to have to cross this at 90 degrees. We're going to have to get really, really steep here to cross at 90 degrees. And as we do that, it looks like we're going to come back around. Doing my best to draw that at 90-degree intersecting angles. Let's try that again over here. We'll start from this side this time, crossing all of these at about 90 degrees. And that must curve pretty steeply to come back there to give us our equipotential lines. So key point, equipotential lines always cross electric field lines at right angles. Let's talk about the potential due to a point charge, just like we talked about the electric field due to a point charge. To calculate the potential difference due to a point charge, the electric potential, well, if force is kq1, q2 over r squared, and we found electric field was going to be kq over r squared, well, potential is just going to be kq over r. The nice thing about potential is it's a scalar. We don't have to worry about direction. We can add them up in scalar form, save us a lot of work. And to find the potential difference due to multiple point charges, we just take the sum of the electric potentials due to each individual point charge. Again, not worrying about any vector nature. Electric potential energy then can be found by multiplying the electric potential by the charge. So electric potential energy due to a point charge is QV, or Q times KQ over R. Therefore, electric potential energy is going to be K times the product of your two charges divided by the distance between them. Let's take a look at a sample problem here. Find the electric potential at point P, which is located 3 meters away from a negative 2 coulomb charge. What is the electric potential energy of a half coulomb charge situated at point P? Well, let's start by finding the electric potential at point P. V at point P is going to be KQ over R, where K is 9 times 10 to the 9th Newton meter squared per coulomb squared. Our Q is negative 2 coulombs, and our distance is 3 meters. So that's going to give us about negative 6 times 10 to the 9th volts. What is the electric potential energy of a half coulomb charge situated at that point? Well, the electric potential energy is charge times voltage, or potential, which is going to be 0.5 coulombs times our negative 6 times 10 to the 9th volts, or negative 3 times 10 to the 9th joules. Nice straightforward applications of those formulas. Let's try one that's a little more involved, kind of mirroring what we did with the electric field. Let's find the electric potential at the origin due to the 3 charges shown in the diagram. And at the end it says if we place an electron at the origin, what electric potential energy does it possess? Now this is awfully similar to what we did when we were finding the net electric field at the origin, but now we're looking for potential. So we're going to do it with the same basic strategy. Let's find the potential at the origin due to each of the 3 individual charges, and then we'll add them up. So the potential due to the green charge, that's going to be KQ over R, or 9 times 10 to the 9th Newton meters squared per coulomb squared. Our charge is 2 coulombs, and our distance from the origin, 8. So that's going to be just 2.25 times 10 to the 9th volts. Now let's do the red charge. V equals KQ over R, which is going to be 9 times 10 to the 9th times negative 2 coulombs over 8, which is going to be negative 2.25 times 10 to the 9th volts. And finally, let's find the potential due to our 1 coulomb charge. V equals KQ over R, or 9 times 10 to the 9th times 1 divided by R. Well, we said last time if we make a right triangle here, that side's 2, therefore the hypotenuse must be the square root of 2 squared plus 2 squared. So R is going to be square root of 2 squared plus 2 squared, or square root of 8, which is 3.18 times 10 to the 9th volts. Now to find the total, the potential here at the origin, we have to sum up the potentials to each of those three charges. So the total is just going to be, well, 2.25 times 10 to the 9th plus negative 2.25 times 10 to the 9th. Those are going to cancel out. That's going to be 0. And all we're left with is this 3.18 times 10 to the 9th volts. So that's the potential due to those 3 point charges when you're here at the origin. Finally, we're asked to find what happens to the electric potential energy if we place an electron at the origin. What's its electric potential energy? Well, let's do that. The electric potential energy due to that electron is just going to be charge times voltage. And our charge is negative 1.6 times 10 to the minus 19 coulombs, because it's an electron, it's negative. Our voltage is 3.18 times 10 to the 9th volts, which is going to give us a potential energy of about negative 5.1 times 10 to the minus 10 joules. But let's point out one other item here. If instead we did this in electron volts, this would have been minus 1e times 3.18 times 10 to the 9th volts, which would have given us negative 3.18 times 10 to the 9th EV. So you can see where using electron volts could be a lot more convenient. But since it doesn't specify which units it wants for our answer, we'll circle both of them. They'll both be correct. All right, let's talk a little bit about parallel plate configurations. Configurations in which we have two parallel plates of opposite charge that are situated a fixed distance from each other are very common in physics because this is how we make a capacitor, an electrical device used to store charge. And the general look of these is, we'll take one plate, we'll put another one just a little bit of distance from it. They have some cross-sectional area A, we'll situate them some distance from each other, D. And then typically we're going to put some charge like positive Q up here and minus Q there. There's the basics of a capacitor. Now the electric field due to two parallel plates, as long as you're away from the edges of those plates, is constant. And the electric field, as we know, runs from positive to negative. So anywhere between these parallel plates, as long as we stay a little bit away from the edges, is constant throughout this entire region. It's given by the voltage, the potential difference across the plates, divided by their distance. Nice, easy way to calculate a uniform electric field. And that's true, E equals V over D. Here, 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 anywhere between those plates, it's constant. The magnitude of that electric field strength is given by the potential difference divided by the plate separation. And the units are going to be newtons per coulomb again for an electric field, or, well, volts over distance, volts per meter. So we're proving that we have the same units. Newtons per coulomb is equivalent to a volt per meter. All right, capacitor is an electrical device used to store charge. It consists of two conducting plates separated by some sort of insulator. That insulator could be air, it could be vacuum, it could be paper, it could be jello. Anything that's an insulator you could put in between the plates and you would still have a capacitor. Now once the plates are charged, they're disconnected. The charge is then stuck on the plates until the plates are reconnected. So if you put a charge on each plate, you create an electric field between the plates. Disconnect them, the charge is stuck there. You've got all that energy that's stored in the electric field. The amount of charge a capacitor can store for some given amount of potential difference across it is known as the device's capacitance, capital C. Now notice capital C is capacitance, but it's also used as a unit of charge, coulomb, so we've got to be careful with our capital C's. The units of capacitance are coulombs per volt, also known as a farad, capital F. And a farad is a very large amount of capacitance, so much more often we'll be talking about millifarads, microfarads, nanofarads, even picofarads. So, our key formula for capacitance. Capacitance is equal to the charge divided by the potential difference between the plates. C equals Q over V. Capacitors store energy. Because the charges are on opposite plates of the capacitor, they exert forces on each other. It becomes an energy storage device where that energy is stored in the electric field. And you can find the energy stored in a capacitor by the formula potential energy in a capacitor is 1/2 times the capacitance times the square of the potential difference. If we write this as 1/2 CV squared, well, we also just learned that C is equal to Q over V. So I could write this as 1/2, and I'm going to replace C with Q over V, and I still have a V squared. So I can do a little bit of simplification here. V and the squared goes away, and we will come up with 1/2 QV is also equal to the potential energy stored in a charged capacitor. So let's do an example with capacitance. A capacitor stores 3 microcoulombs of charge, Q equals 3 times 10 to the minus 6 coulombs, with a potential difference of 1.5 volts across the plates. V equals 1.5. What is its capacitance and how much energy is stored in it? Well, its capacitance, C, is Q over V, or 3 times 10 to the minus 6 coulombs over 1.5 volts, is going to be 2 times 10 to the minus 6 farads, which is 2 microfarads. How much energy is stored in the capacitor? Well, we could do this a couple different ways, but let's start off with 1/2 CV squared. That's going to be 1/2 times, we just found our capacitance, 2 microfarads, or 2 times 10 to the minus 6 farads, and our potential difference, 1.5 volts squared, gives us 2.25 times 10 to the minus 6 joules. Or we could have used U equals 1/2 QV, which will be 1/2 times our charge, 3 times 10 to the minus 6 coulombs, times our potential difference, 1.5 volts, which amazingly is 2.25 times 10 to the minus 6 joules. And of course, those have to be the same. We said the formulas were equivalent. All right, looking at the charge on a capacitor. How much charge sits on the top plate of a 200 nanofarad capacitor when charged to a potential difference of 6 volts? Well, let's start there. C, capacitance, is 200 nanofarads, or 200 times 10 to the minus 9 farads. Potential difference, V, is 6 volts. So if C equals Q over V, then that means our charge, Q, must be CV, or 200 times 10 to the minus 9 farads times our potential difference, 6 volts, which is going to be about 1.2 times be your dielectric constant, K, times epsilon naught. And materials have larger Ks. Air or vacuum, that's going to be 1, so epsilon is equal to that. If you have something that's a little bit more resistive, a better insulator, for example, that's going to be a bigger number for K. So that will increase your capacitance as you put a different insulator in there. Let's see how that works. How far apart should the plates of an air gap capacitor be if the area of the top plate is 5 times 10 to the minus 4 square meters and the capacitor must store 50 millijoules of charge at an operating potential difference of 100 volts? Should say must store 50 millijoules of energy. That makes more sense. Well, if our area is 5 times 10 to the minus 4 square meters, and our potential energy is 0.05 joules, we have a potential of 100 volts. Let's see what we can determine here. Well, U equals 1/2 CV squared, but we also know that C is equal to epsilon naught A over D. And because it's an air gap capacitor, I can leave that epsilon naught. I don't have any dielectric constant I have to put in front of it there. So that means that U equals 1/2 times epsilon naught A over D times V squared. If I rearrange this a little bit to find how far apart or the distance between them, I would say that the distance then, solving for D, is going to be epsilon naught times A times V squared divided by 2 times the potential energy, which is 8.85 times 10 to the minus 12 times our area, 5 times 10 to the minus 4 square meter, times our potential, 100 volts squared, divided by 2 times 0.05 joules. When I do all that, I come up with a separation distance of about 4.43 times 10 to the minus 10 meters. Just combining our formulas in order to solve for an unknown. Let's do some more capacitance calculations. Find the capacitance of 2 parallel plates of length 1 meter and width 1 millimeter and width 2 millimeters if they are separated by 3 micrometers of air. All right, to begin with, capacitance is epsilon naught A over D. It's an air gap capacitor, so I don't have to worry about a dielectric constant there. That'll be 8.85 times 10 to the minus 12 times our area. Well, that's going to be length times width, or 0.001 meters, times 0.002 meters, all divided by the separation of the plates, 3 micrometers, or 3 times 10 to the minus 6 meters. Put that in my calculator, and I come up with about 5.9 times 10 to the minus 12 farads, which is also 5.9 picofarads. Now, what would the device's capacitance be if we replaced that air with glass, which has a dielectric constant of 3.9? Well, the only thing we have to do there is, if before C was epsilon naught A over D, because we're no longer using air or vacuum, because we've got a dielectric constant of 3.9, 3.9 epsilon naught becomes my permittivity. So now all I have to do, all of this is the same as multiply my answer by 3.9. So that's going to be 3.9 times 5.9 times 10 to the minus 12 farads, or 2.3 times 10 to the minus 11 farads, which is 23 picofarads. So by inserting a dielectric, material with a higher dielectric constant, I increased my capacitance. Because the dielectric constant was 3.9 times larger than the original, my capacitance is 3.9 times larger than the original. All right, let's go through a couple more problems, make sure we've got everything down. An electron sits on an equipotential line of 5 volts. How much work is required to move the electron to an equipotential line of minus 25 volts? And let's make this one easy. Let's do it in electron volts. Well, as we do this, the potential energy is equal to charge times potential difference. The charge on our electron is -1 elementary charge. Our potential difference, if we go from 5 to -25 volts, well, delta V is final minus initial. So that's going to be -25 minus 5, or -30 volts, which will give us 30 electron volts. Nice and straightforward. Let's take a look at conservation of energy as we talk about these problems. A proton is held at a fixed point in space where the electric potential is 500 kilovolts, or 500,000 volts. The proton is then released. Assuming no energy is lost to non-conservative forces, what is the speed of the electron at a point in space where the electric potential is 100,000 volts? A conservation of energy problem. It starts out initially with electric potential energy, and that must be equal to its final electric potential energy. And where did any excess energy go? That must be the final kinetic energy of our proton. Well, we know the initial is going to be Q times our initial voltage. That must be equal to Q times our final voltage, and our kinetic energy is going to be 1/2 mv squared. So as I start solving to get v squared all by itself, I could say then that v squared is going to be equal to Q VI minus VF. I'll have the 2 in there, so 2 will factor out the Q. VI minus VF divided by M must be equal to v squared. Therefore, v squared equals 2 times our charge on our proton, 1.6 times 10 to the minus 19 coulombs. VI minus VF, that's going to be 500,000 volts minus 100,000 volts, all divided by the mass. Have to look up the mass of a proton. You'll find that it's about 1.67 times 10 to the minus 27 kilograms. Plug all that into my calculator, and I come up with something around 7.66 times 10 to the 13th meters squared per second squared. So if I want just velocity, I take the square root of both sides and get that v is equal to 8.75 times 10 to the 6th meters per second, converting electric potential energy into kinetic energy. All right, let's take a look at a problem with 2 conducting spheres. These 2 conducting spheres, each with charge Q, are connected by a wire as shown. Do any charges flow between the spheres, and how do their potentials compare? Well, the first thing we have to realize is when we connect them by a wire, all of a sudden they must be at equal potential. Anything that's connected by a conductor is going to be at equal potential. So once we do that, these have to be at the same voltage. That means if we look over here at Q1, V1 equals K Q1 over R1. Over here on the right-hand side, V2 equals K Q2 over R2. And because the potentials must be equal then, we could say that K Q1 over R1 must equal K Q2 over R2. Nice simplification we can make there. Divide K out of both sides. Therefore, Q1 over R1 equals Q2 over R2. And since we know that R2 is going to be twice R1, measuring those lines, we could figure that out, then Q1 over R1 must equal Q2 over 2R1. Or a little bit more rearrangement to say that Q2 must equal 2R1 Q1 over R1, or that's going to be just 2Q1. Q2 is equal to twice Q1, then we must have charge flowing from 1 to 2. So our charge must be flowing that way. We'll have charge flowing from Q1 to Q2. How do their potentials compare? They gotta be equal. Equipotential lines for a capacitor. Draw the equipotential lines for the parallel plate capacitor below. Well, the first thing I'm going to do is it's probably easier to draw the electric field first, going from positive to negative. So I'll put in some electric field lines first, in green here. Electric field is constant between those. And then we know that equipotentials are always crossing electric field lines perpendicularly at right angles. So I could draw my equipotentials that way. And if this is 0 volts, that'll be maybe 1, 2, 3 volts, 4 volts, 5 volts. We've got a constant electric field between these, but we don't have a constant potential. The potential is going to have a linear gradient from 5 volts down to 0 volts. All right, hopefully that gets you a good start on electric potential difference. We talked about electric potential energy and even some capacitors in there. Thanks so much for your time, and make it a great day, everyone.